A very hearty good evening to all the participants present out there. The Center of Excellence in Safety Engineering and Analytics, IIT Kharagpur, welcomes all the participants to the weekend talk on safety engineering management and analytics. This program is conducted under Azadi Ka Amrit Mahotsav, which is conducted from the central government commemorating the 75 years of India's independence. So as usual, we start our program with this beautiful shloka, Asatoma Sadgamaya, Tamasoma Jyotirgamaya, Mrityorma Amritam Gamaya, which inspires us to lead from ignorance to the truth, from darkness to the light, and from death to immortality. So with this, myself, Moom Mitra from Tata Steel, Sinjana, Souvik, and Ashish from IIT Kharagpur are the co-moderators of the session. Welcome all of you. And we welcome all the dignitaries on the virtual dais. So today we have a very eminent speaker with us, Dr. Mark Leto. He is the professor of Industrial Engineering, Purdue University. So Dr. Mark Leto is the co-chair of the Interdisciplinary Graduate Program in Human Factors. Dr. Leto's research and teaching interests are in the areas of hazard communication and decision support. He is particularly interested in methods of increasing the effectiveness of information provided to consumers and workers. In 2008, he published a well-received textbook entitled An Introduction to Human Factors and Ergonomics for Engineers that synthesizes years of experience in the field of human factors in teaching, research, and engagement with outside organizations. So, ladies and gentlemen, the lecture today will be quite interesting. With this, I request Maiti sir to formally welcome our expert speaker.
Yeah, thank you. So, just before welcoming, I just tell something about Professor Leto. Professor Leto, what Mom has already mentioned. In addition to that, some more like he was former head of the School of Industrial Engineering at Purdue University, co-chair of Interdisciplinary Graduate Programs in Human Factors Engineering, and he has been there in Purdue University for about 30 years. He was also Director of Discovery to Delivery Center at Purdue University. And Dr. Leto's research already Mom has mentioned. And he has taught and developed several different undergraduate and graduate courses in Purdue, including safety engineering, decision analysis, and engineering economics. And he has been actively engaged, consulted, and collaborated with industry for several years, including large companies such as Procter & Gamble, Liberty Mutual, Medium, and sized company through industrial consultation program at Purdue, technical assistant program, and in Indiana Manufacturing Competitive Center. With this, I welcome Professor Leto, and I now hand over. Also, I welcome all the participants for this CoE-SEA weekend talks. This is the 18th week, and now I hand over the that's introduction introductory part to Professor Gaurav Nanda for Dr. Mark Leto's speech. Yes, Dr. Nanda.
Hello everyone, and welcome to today's lecture. And today, so Professor Leto will be joining shortly. He had got a doctor's appointment he had to go to. Read his presentation, and I'll play that recording. And meanwhile, he will join anytime because his doctor's appointment will get over at any time. So I will play the video now, and hope you all will be able to hear and watch the video. So let me share my screen.
I'm a professor at Purdue University, and I would like to talk today about some of the work we've been doing over the past several years on assisting human coders when they assign injury narratives to various standard categories that are used in some of the surveillance coding systems that are out there. So the title of my presentation is Evaluation of the Impact of Machine Learning-Based Decision Support on Coding Accuracy and Coder Workflow in a Real-World Injury Surveillance System. And so this particular project is one that we've been working on with a team of people from Australia and Purdue here in the US. And so at Purdue, it's been myself and Professor Nanda, who also gave a presentation to you guys earlier. From Australia, we have Jasani Catchpool from the Queensland Injury Surveillance Unit and Professor Valmore from Queensland University of Technology. And so to give a little background into some of the kind of work that we've been involved with, it turns out that a lot of organizations across the world collect injury data for surveillance and other purposes, and they assign these various codes. And so there are many different coding systems. I won't bother getting into these in detail, but in the case of the project we're working on with the Australian people, they were particularly interested in assigning 4 different types of codes, which were listed here: the external injury codes, also a more detailed code on some major contributing factors, the nature of the injury itself, and the mechanism of the injury. These are all different things that they're assigning. And so some of this is done within the emergency departments by personnel there, nurses and other staff who fill out some of this. But a lot of it ends up being assigned later within, in this particular case, in the case of Queensland, Australia, the Injury Surveillance Unit themselves have a set of coders who assigned categories to the particular cases that come in. And just to give a little feel for what are some of these codes, this slide shows some of the external codes that are assigned. So for example, motor vehicle, whether it was the driver or passenger of a vehicle, motorcycle, bicycles, pedestrians, animals. It's a pretty long list of external causes that they work with. And within that, they also move on to some much more detailed codes, such as the major injury factors, which can be roughly mapped to the objects that cause the problem. And this is just a broad overview of the categories. Within each of these, there are many different subcategories. And so in the work that we were dealing with, we were looking at maybe around 160 or more of these more detailed major injury factors that have been assigned. They also have intent codes that we mentioned earlier. Was it an accident or was it self-harm? And so anyway, that's another code that is worked with that includes some sub-breakdowns coming down to various kinds of assault, etc. And they have the mechanism of injury codes, which are at a more detailed level, looking at exactly how the injury happened, the nature of injury itself. These are all things that are being assigned. So many different types of codes are being assigned in these systems by the different coders. One of the problems, of course, is that it takes a fair amount of time to assign these, and quite often the classification schemes are fairly complicated, and the code books that explain how to assign everything can run into hundreds of pages. And so the fact that it's something that requires a fair amount of training translates into problems when you have untrained people assigning these codes. So hospitals tend not to necessarily have the necessary expertise. So a lot of the times the codes aren't assigned at all, and the coding, government coding groups that later on look at these have to deal with that. And so anyway, there are some issues related to the fact that it takes time and it's not necessarily that easy to do. And so one of the approaches that's attracted quite a lot of interest over the years, we've been working on some of this starting with some of my early work with Liberty Mutual, insurance provider in the U.S. Go back at least 25 years to some of the first work that we did, where we tried to assign some of these codes using naive Bayes. And so that was one of the first modeling methods that we applied. Later on, moved on to some other approaches, including some of the deep learning methods and whatnot as well. Now, Dr. Nanda talked about some of those projects that we've worked with. One of the interesting things we've seen is that, well, there's quite a lot of diminishing returns with the more complex models. They don't necessarily work much better, or maybe don't even do better than some of the simple models like logistic regression. Naive Bayes tends to be a little behind, but surprisingly enough, even a good naive Bayes model can be quite effective. But none of these models, unfortunately, are really quite good enough to rely on alone. So somehow you need to come up with something that works a little bit better than just the models themselves. So we'll talk a little bit about some of these other studies that have been done. So to summarize some of the earlier projects, I've listed many of these are projects that we, for example, the work with Wellman, Sorok, and Smith, for example, was back when we were working with Liberty Mutual. And so that was some of the earlier studies. We actually did some even earlier work back in the 90s where we first tested some of these naive Bayes methods in particular for assigning like construction work zone accidents to various categories. So it goes back a long way, some of the early work that we did. And the approaches have actually worked surprisingly well. If you look at some of the numbers that we're looking at here, numbers, overall sensitivity of the predictive models has been quite good, but the unfortunate reality though is that they're really good, but they're really not quite good enough. I mean, if you really think about it, 80% is remarkable that just some simple model like naive Bayes or some variations of it can duplicate the human coders with 80% sensitivity. But a lot of the earlier studies were maybe around 70% or a little lower, but very promising, very tantalizing, but just really not quite to the level that we really want to be. So one of the things that we looked at in more recent years are what can we do to improve performance so that you can somehow take advantage of the machine learning models and somehow deal with the fact that they don't work quite as well as what we really want them to perform at. And so some of the kind of issues that we see there is that, well, the models tend to have very high sensitivity for the large categories, but especially the small, very rare categories tend to be very poorly predicted. And at the bottom line, it's a very hard problem from a modeling perspective because you have a large number of categories and they're extremely highly skewed. And so just to illustrate this effect, we have some data here from Australia where we're looking at different kinds of E-codes that were being assigned. And if you look here, for example, falls on the same level are really a huge chunk of the data. Then you have a lot of these other ones that are very, very small. And so firearm, for example, are a very small category. They have a few cases where people are injured with guns or weapons of that nature, but very small. Even things like submersion, drowning in the swimming pool, they're very small compared to these larger categories, such as the falls and the struck by type of incidents. And that, of course, means that you have a very difficult classification problem. So it's not surprising that the models are not doing as well as you would like, if you just simply guess the large category, you can get a fairly good performance just by doing that, but you don't necessarily have the ability to really get all these small categories that are really kind of the interested ones. And another problem, of course, is that, well, the descriptions that the people are working with the ER, emergency rooms, are often relatively brief, sometimes incomplete. Maybe there's some problems and that some important information was left out. And so maybe the narrative only described the injury, but it didn't describe what caused the injury. So you have all these kinds of issues that create problems, as well as very, very messy data sets, huge data sets, where we actually did some linguistic evaluations, and we observed that, well, over half of all the words happened only one time out of a data set of 500,000 cases. And so you have this extremely noisy data that you're working with, where you have just a lot of problems that you have to try to deal with. And so it's not surprising that the models themselves aren't doing as well as you might hope. And to make it even more difficult, there are often some coding errors in the data sets as well. So expecting a machine learning model to perform at an extremely high level of accuracy is unrealistic. There are just too many issues, just starting with the nature of the data that you're working with. And so what we wanted to think about are there some strategies that we could follow to somehow take advantage of what the computer does and what people do. And so we looked at many different kinds of filtering methods, and the basic idea is that, well, maybe we can use machine learning models to code a subset of cases and then leave the rest for the human coders. And that was one idea that we worked with, and we did, I'll give you a couple of results in a few minutes here, quite successful at, where we can basically pull out a relatively large chunk of cases that are codable by machine learning models and then have people do the rest. The other idea, of course, is that, well, maybe we can improve the human coding as well by using the machine learning models as a form of decision support, where you get basically a team. You have the machine learning model working together with the human coder, and hopefully we could actually get better performance than if either was performing alone. And so these are really kind of the two different strategies that we went with. And so the filtering approach is something that we've been talking about for many years, but in this case study, we'll talk a little bit about some of the work that we've done with actual coders, where we provide them information predictions from the models and then see what happens. Does that actually help the coders? And so some of the different kinds of filtering methods that we work with, then one of the main things we looked at is, well, some of the models like logistic regression and naive Bayes will actually provide a probability estimate of how likely the prediction is to be correct. And so various prediction-based strategies, as well as ensemble methods where you look for agreement between multiple models. And so somehow flagging the cases that are likely to be incorrect and then giving those to the human coders is one strategy that we went with. And to illustrate how this worked, we did several different studies. This is just one of many that we did. We had many others that we did with Liberty Mutual and other organizations, including the Bureau of Labor Statistics and whatnot in the U.S. But we did a study where we had basically 500,000 cases of these incidents basically at emergency rooms where people came in with injuries. And so we had data on what was actually assigned by the coders to these. And so the basic idea is that, well, we have that data, so we can try to learn from that data and try to assign codes to various models. And so here, for example, we have 3 different models that we were looking at to assign major injury factors. Here we have about 156, actually, depending on which year you could have more or less major injury factors in your data set. But we have a long list of factors ranging from various kinds of drugs to various kinds of toys to various kinds of animals. It's a very, very long list of things. And you can see here that the models were able to predict these with a fair degree of accuracy. I mean, sensitivities of ranging from 0.56 for multinomial naive Bayes to 0.71 for logistic regression. And by the way, we did try some other methods like deep learning and whatnot, and we get results that are almost identical to what you get with the logistic and support vector. But that's a whole other topic. And as you might expect, if we group categories, we can get the performance up even a little better. But still, these numbers, if you think about it, you know, they're good, but they're really not. I would hesitate to say they're good enough. And so we looked at then some of the different kinds of filtering strategies, and this slide just shows some of the results that we had with a huge set of decisions, filtering strategies that we looked at. And so we included things such as hierarchical clustering, we've been basically filtering on different prediction strength. Here, for example, was a strategy that had a very nice bump in performance where we had expert rules combined with prediction strength. So looking for cases that had a strong prediction strength plus using a rule-based filter that was expert-based to try to flag some of these problems that coders often had. And you can see here that, well, with about 25% filtering, we could bump up the sensitivity up to over 90%. So you get a very nice improvement from, you know, just the base number. And so this is something that was encouraging. And so, yes, clearly you can filter out a lot of cases where the machine learning models are going to be correct. And so some of the other strategies where we even filtered out more cases, just using prediction strength, it's not as good as, you know, bringing in the expert rules, but the expert rules, of course, take a lot of work. And so clearly that's a very labor intensive type of strategy. But even with just some type of prediction strength-based filtering, you can see here that we're getting a very nice bump with about half the cases being filtered out. And so you filter out half the cases and just keep the machine learning prediction, and the rest you have the human do. So this is one approach. And filtering clearly has some advantages, but you still have a large set of cases out there that need to be worked with. So it's often suggested that more training data is going to solve the problem, but based on what we see, that's clearly not the case. With the better models, you're still plateauing out with a relatively large set of cases that are not being assigned. So the models alone, throwing more data, isn't going to necessarily solve all the problems. So here, I mean, training a model with 450,000 cases, way off in this extreme, you are getting good performance for basically all the models. But what's problematic here is that when you do the unweighted, you're still missing the small categories. And so you're getting better and better with the larger categories, but the small ones are not necessarily improving very much. And they plateau out at a much lower level. So that is a problem. And that's where some of the other ideas that we work with come into play. So what we looked into was providing some type of machine learning-based decision support to the coders themselves. And so we were working with the Queensland Surveillance Unit, who has a set of expert coders. And so providing some assistance to them as they go through the process of assigning the codes. Kind of get a quick view of what they're doing. Here's this typical screen where we see the information that's being provided. You have the narrative here. Somehow you need to figure out how to assign all these other things to it, such as the cause, the intent, so you can see there's a long list of things that you're assigning. Our focus, of course, was on the mechanism, the intent code, the external cause codes. And so we focus more on some of the other ones, but theoretically you can do many other ones, but location and some of these other ones are maybe less likely that you can actually pull out of these codes. So if you look here, it lists, for example, a motor vehicle, MVC, motor vehicle collision, driver injury. And so it's a lot of information mixed up in here with regard to what happened. And it also includes information about the treatment. And that's another reason why machine learning models will have some difficulty. Sometimes, clearly, a lot of the injuries are caused by drugs as well. So an overdose of paracetamol, for example, is a fairly significant reason why people would go into ER in the first place. So what we did is we developed some tools that actually assigned codes. So the text miner program is something that we developed that assigns the external cause, the major injury factor, the mechanism, and intent using the narrative. So if you go back here, you see you have a narrative. You basically take those words and you make predictions. And so we took two different models, logistic and naive. One of the reasons we took naive is that even though it doesn't really perform anywhere near as well for the overall sensitivity, quite often it's better on some of the small categories. And so it is interesting that you do get some extra bump by looking at the naive Bayes model as well as the logistic. And so basically the models work fairly well in our previous studies, but like I said, they're really just not quite there. They work well, but they're not quite as what we would really want. So in terms of the basic idea of what we have the manually coded data coming in from the ER, and you basically learn from that and then make predictions. And so the text miner program just takes the text descriptions and generates categories, predicted categories along with probabilities. And so it allows them, for example, they could pick which modeling method, or they can do a combination of methods, and then basically you get the outputs and work with those. And so we set up different options. We set things up so that you could actually generate like a list of the top predictors, and we set up different modes like a batch mode and a single case mode. And so to see how some of these works, we'll show a couple slides in a second here. But the basic idea here is that, well, we set it up so that it would flag cases for manual review. And so one way of flagging it was the filtering idea that we talked about. So for example, if the probability is less than 0.5, for example, it would flag that as a case that somebody should look at. And so that was one strategy that we worked with. And so another aspect of those is that we can give the coder a list, like maybe the top 5 predictions, and let them look at that. And we can add the extra filter where the ones that are extremely strongly predicted, the user doesn't have to look at those. And so we trained this system with data from different years, and then did a number of studies where we tested how it worked. And that's where some of the filtering work that we looked at earlier came back to. But to show how this works, one mode we had is what I call the quick classifier mode. And so this is just an item by item. So here we have an injury description, a single description, and the person selects, in this case, he said, well, I want to classify that using logistic regression, and I want to assign the external cause code. And in this case, they wanted to use some pre-processing rules that we had in the data set as well. We hit the button classify, and then this is what it spits out. And so you can see here, it's relatively reasonable that, well, yeah, this was a fall, and it was a very high degree of confidence. And so if you look here, somebody slipped on a wet floor, and so it worked. And this is typical, I mean, for these types of incidents, the fairly common incidents, the accuracy is really good. You can see here that it also lists some other things with very low probabilities, but clearly it's 95% confidence. It's pretty sure that this was a fault. Well, we also had what I said we call a batch mode, which is a different way of doing things that fits better into the workflow of the coders, because all this stuff comes through a pipeline where the records are coming from the hospitals and then they get pre-processed and sent to the coders. And so we set up a batch mode system that could actually take a large batch of records and assign codes, and also assign filtering thresholds, and also assign multiple outputs. And so here, for example, you can see we have somebody's assigning using logistic regression, the external causes, or you could do everything all at once. So a batch mode, you can, in terms of workflow, I mean, you can do everything all at once, or you can do one at a time. And it can assign like a single output or a top 5 to each one of those code groups, and also can tag them with filtering tags based on a strength. So here the default is, well, everything is a 0.5, but you could also do a product filter where you consider the strength of everything. But that's actually interesting. We also set this up so that it can also read records from two different, some hospitals use the EDIS system, others use the FirstNet coding scheme, and so they code things a little bit differently in the different hospitals. So one thing the system would do is it'd look for whether or not the codes have been assigned already, as well as, and so if there's a blank code, that would be a different situation than if the nurse had already assigned something. But anyway, that's the basic idea of how that worked. And so this slide here shows the overall workflow then. And so what we have here then is here, for example, the EDIS system. So hospitals that use the EDIS system, their records come in, and then we assign auto codes using the batch processor that we just showed, and then basically it feeds into the other system that then presents cases to the coders, and then the coders assign those basically. So what we did then is we did a study where we wanted to look at, well, what would be the impact of adding this type of decision support into that workflow to the coders. And so we expected that you'd get some benefits first by increasing the coding efficiency by actually assigning codes to, especially the easy to assign codes, eliminating the need to do that. But we also expected that by providing suggestions, you would actually improve the accuracy of the coders. So two different things we wanted to look for. And so we actually conducted a study then using data from different months. And so we compared how long it took and how accurate the records were in two different months. And so that was something that we then worked. And so we implemented the system and just looked to see what happened. And so we extracted these data records and set up a control data set. So the February was a control that we then compared to see what happened after we added the decision support. So the basic idea was that, well, if we provide this support, we should get some improvements in efficiency and accuracy. And so it then ended up that we had a subset of cases and that were being assigned. And in particular, one of the things we were looking at were cases that did not have, that weren't assigned in the ER rooms. One thing that we're looking for is a flag for focusing the analysis on. And so So when we go back and look at that, you can see that there's some of the fields tend to be assigned more often in the emergency rooms, and so the external cause code and the intent tend to be assigned more often, but the major injury factor, which is actually the hard one because there's so many possible answers, were much less likely to be filled. So down here we can see that about 46% of the external cause codes were assigned 60% of the intent of injury, and only 2% of the major injury factors. And so in terms of getting the cue, when the coders at the surveillance unit are assigning things, you can see that they were much more likely to have a pre-existing code already assigned for some of the categories and some of the others. And in particular, intent was one that the nurses found relatively easy. They can say that, well, this was an accident or this was self-harm. So this type of coding is relatively easy because there aren't that many possible codes to assign. But the difficult codes like the major injury factor, the coders somehow have to rely on the narratives. And so it's a difficult task at the surveillance unit. So the coders are facing a pretty hard problem, really. And so our overall approach then was to just compare then what happened in the control month and the trial data set, so February versus March. And one problem we had was that it was hard to get the time, say, we weren't actually able to get it specific for each one of the individual code categories, going to get it for the larger record due to an artifact in how the system worked. But we still were able to figure out how much time it took to assign a total record. So if you look at the total record, you have to assign those multiple codes. And so we're getting an aggregated measurement of time. But on the other hand, we were able to come back and look at the accuracy of each individual field, each individual code separately. And so we'll talk about this a little bit later. And so this basically is what we did, is we tried to extract a time, which was really just a kind of an aggregated time for each individual record. And then within that, we were able to get an accuracy measure on the individual fields as well as a supplement. And so just to get a rough feel for what was happening, this bar chart shows that, well, comparing with or without providing the machine assigned codes to the human coders. And again, remember, this is at the surveillance unit level. This is not at the nurse or at the ER level. We see that we have a larger set of cases that took less time. So the blue bar corresponds to the codes that are assigned quickly. And so many more were assigned within less than a minute when they had the machine assigned code. And similarly, there were less cases where it took a long time. So as expected, we're seeing an overall trend there, which we could then break out in more detail, looking at the means for the individual, for the records themselves. So the mean time, which I'll give that in a few minutes, but we do see a bump in terms of being able to code those more quickly and more accuracy. And so in terms of the efficiency, then we can basically just compare the time. And so we saw an increase in cases that were coded more quickly and fewer cases that were more time. And so overall, that works out to about a 13% reduction in manual coding time. So clearly, just providing that prediction was helping the coders. They were able to get the answer more quickly. So from the efficiency perspective, we were seeing some improvement. And so clearly there could be even more complex versions here. We were basically showing them the prediction for each case. We could have actually also get an additional bump by just not bothering to ask them to look at the ones that were extremely obvious. So this is really a conservative estimate how much time saving you could get. So if you remember some of those filtering studies, we could get really good accuracy with relatively small number filtering. So you could even drop out, maybe another 1/3 of the cases that would just be clearly correct. You wouldn't have to even look at it. So that would be in addition to this 13% that we're talking about. So that's one part of it. And so we can then also go back, and like we mentioned earlier, a future study, we could go back and get a more specific answer on the particular field. And so were the improvements more on the major injury factor, or were they on the intent, for example? And I think it's, from my perspective, it probably must be on the major injury factor, because that's really the more difficult one to assign, but that would be something we'd look at a little bit later. And so clearly the more frequent codes, like the more obvious accident, obviously are very easy to put into the accident category as far as intent goes, for example. So those are things that you could probably just totally automate. Now, the other part that we looked at in terms of our analysis, again, is coming back then to the accuracy part of the problem. And so what we did is we brought in some, what you might call super experts, to go back then and look at the codes that were assigned when the coders at the surveillance unit were assigning the codes. And so note that here, we looked at each month separately, the control month and the trial month, and we asked the expert coders to come back in and look at what was being assigned by both the machine learning model and by the coders at the surveillance unit. So the super experts are really what we would call our gold standard. And so we're looking at cases that were agreement or disagreement with the gold standard. And so then basically we went through and did various kinds of statistical analysis of our results to try to get a feel for what was coming out in terms of the trends and whether or not they were statistically significant. And so we did both various types of t-tests, and we also did some kappa statistics in addition to look at the concordance between some of the different sources. And so what's kind of interesting here is that, well, if we start with our control group, when we look at the concordance between the gold standard and the coders at the surveillance unit, this is really our control group. And when we compare against that, we can look separately at intent, major injury factor, and external codes. But if we look at intent, for example, we see that with the machine learning code or machine learning prediction, that the sensitivity went up a little bit when the coders were provided an input. We also looked at, well, how much agreement there was between the gold standard and the classifier, and so you can see the classifier is actually doing very well. It's agreeing with the gold standard very well for this particular category. And the original coders as well are agreeing with it quite well as well. And so the overall performance, we see it's not a huge, if you just look at the overall numbers for intent, you don't really see much of a change in overall accuracy. But it's interesting that when we did the kappa statistic, we did see higher agreement between the gold standard and manual code. So note again, this is only for the accuracy on intent. Remember, I said intent was really probably the easiest thing to assign because there are only a few intent categories. And so accident, self-harm, assault, or other. So it's a relatively easy thing to assign. But even here, the kappa is showing that there's higher agreement between the gold standard and the manual coding when the manual coders were given the prediction that the model suggested. So in a way, you could think that the model was acting as a reminder. So if the coder disagreed with what the model was predicting, it made them think about it. And so that way, and the part of that comes back to is that, well, the human coders were actually correcting some of the mistakes that the model was making. You get a much stronger effect, though, when you look at, well, what happens for E-code and what happens for the major injury factor. And so here for E-code, we're getting much more obvious bump. Here, about a 2% bump. And so again, we're seeing improvement. And so even in the overall numbers, we're seeing an improvement for E-code, which is a more difficult category, about 30 categories as opposed to the 4 categories. And the kappa statistic also supports the fact that you're getting an improvement. And so we could also look at the results separately for the major injury factor. And here we see that we have an even greater bump, about a 3.5% bump in accuracy by just showing them the prediction. So the decision support is very simple. All we're doing is just showing them the prediction, and that's helping the coder give a more accurate answer. And that, of course, is what we're hoping to see in terms of accuracy. And so to summarize that, by providing this relatively simple decision support tool, which is just a prediction, we get a reduction in time, and we also get an improvement in accuracy, overall improvements. And so this again is something that if we work that through in terms of the previous numbers are basically the weighted accuracy, but if you look more at just the overall, where you take into account the really small categories, the bump seems to come out a little bit better. So anyway, we are getting an improvement both in terms of time and accuracy when we provide that machine learning prediction to the operators, or the human classifiers. So it's a promising result. Clearly, we want to do a little more to get a more precise estimate of that. And so in particular, you can look at the where is the time improvement coming? Is it, as I might expect, is it really related to the major injury factor? But that would be one thing that we could look at. It also turns out that one of the things that we weren't really thinking about, but at the time in the COVID time period, one of the nice features of this is that we could just run the machine learning model without worrying about whether or not the predictions were perfect. And so that just getting a quick answer for a year's worth of data would take like 6 to 12 months of human coding time. And this, of course, if you just ran it on the model, would just take a matter of a couple hours or so. So that was actually kind of an interesting side note, is that, well, if you don't need something that's as accurate as what you eventually want to publish in your final tabulations, you can get a very quick rough estimate. So that's another strong benefit of this particular strategy that we've been working. And so anyway, that's the study. Promising results. Clearly, we need to do a little bit more. And I do think that we can get much larger improvements on the time reduction by bringing in some additional filtering, as we mentioned a few minutes earlier. And so hopefully we'll be able to answer questions. I'm planning to call back in after the video finishes, and so we'd be happy to take some additional questions at that time. Thank you very much.
Thank you, sir. So very informative session. I think, sir, next we can move on to the Q&A. We've seen many questions in the chat. So I request one of our co-moderators to please take up the Q&A.
Yes, sir. Yes, thank you. Thank you, sir. The lecture was very informative and very interesting. So we have found a few questions in the chat box. So I am taking one by one. So first question is, what are the different stages of DSS and how to architecture it?
Yeah. So are you able to hear me?
Yes, sir. Yes, sir. You are audible.
Yeah. So yeah, I was trying to call Professor Leto to check if he's able to join, but it seems like he's still at the doctor's place. So he did not pick up the call. So maybe I can help answer those questions. So regarding the architecture of the decision support system, the thing is that they have a system, an online system. So if we go back a little bit over here, yeah, so this architecture over here, so they have data coming in from two main sources. One is from the hospitals and one is from other agencies. And so this has to be integrated into their system. So they had built the system using C# and this text miner tool that Professor Leto mentioned, that was developed in Microsoft Access. So the interchange between the two systems is currently being done through file transfer mostly. So the files are coming from different systems, and then the text miner is processing those files and giving them as output, and that output is taken by the coding system that the people at the Queensland Injury Surveillance Unit were using. That coding system was modified to show the prompt or suggestion of the code that is recommended by the machine learning model. So that was kind of the challenge was not to disturb their usual flow, but include that aspect of decision support in the usual workflow that they were doing. So at different stages, when they were going to assign codes on external cause, then mechanism and major injury factor, the prompts were new fields were created and prompts were being set for that. So
Yes, sir. Yes, sir. Thank you, sir. Now I am moving to the second question. What were the reasons for specifically considering February data as a control data? What impact to the result will be if we consider the data of a summer month or data of a winter month? Yes, sir.
Yeah, that's a good question. So, the main reason February data was considered because that is when we started implementing this feature. So this is like a pilot study and initial results that we have got. Ultimately, we are planning to do a larger study, which will if we take 1 year of data as the basically entire without coding, and another set of coders which we give the year's worth of data with coding, then that variation due to season that will be absorbed in that. But currently, February and March, there in Australia it was kind of summer season, so the weather did not change much. But yeah, it is true. In winter, if there is snow, then the nature of accidents will change. And if it is summer, the nature of accidents change, like insects and bug bites, and a lot of sports injuries happen in that season. So yeah, so that is true. And in coming days, when we have larger data sets to test, we will test them out. Usually there is a 6-month lag between when the data is received by the surveillance unit. So we have to factor that in. But yeah, that's a good point.
Yes, sir. Yes. Thank you, sir. Now the next question is that for this kind of injury information, Is there any standard dictionary available, or it is a manually annotated data?
Yeah, it is manually annotated data. So standard dictionary, we have not found like anything. There are some public databases like the NICE database that is there in the US, which is about product injury database. Then there is another one in the US, National Health Injury Survey. And I have seen like couple of data sets that are from South America, like from Brazil, which are public injury data sets. This was trained on basically manually annotated data. And we can understand, if we train it on same set of data from same set of sources, there will be better consistency between the training and prediction sets. But if the training has been done at some other geographical location, there might be the performance may be impacted because of that. But overall, for the larger categories such as like fall and struck, the intuition is that it will still work okay. But some of the uncommon injuries, they will be differing from different geographies as well as cultures and the kind of lifestyle that people have. So, yeah.
Yes, sir. Yes, sir. Thank you, sir. Now the last question is, sir, to improve the decision support tool accuracy, what are the steps we can follow?
So one of the main steps is having good quality training data. So what we are trying to do is also identifying inconsistencies in manually coded data. So like when we look at similar descriptions, but they have been assigned different codes by different coders. So those kind of inconsistencies, they lead to deterioration in performance of machine learning model and subsequently the decision support system. So that is one of the steps of, just a minute, I'm getting call from Professor Leto. So I'll just check if he's able to join.
Yeah, hello?
Yeah, Professor Leto has joined.
Hello.
Hello?
Good morning.
Hello?
Good morning, Professor Leto. Good morning.
The reception. Good morning. Yeah, good morning. Sorry about the delay there. I got an unexpected delay there, but at least try to touch base if there are any additional questions.
How are you? How are you now?
I'm doing fine.
Yes, the lecture, the video or recorded PPT we have shown, actually played that one, and it was very well prepared and well presented, and the participants are very happy. And we are now actually at the end of that question answer session. We are extremely thankful to you that you have taken a lot of pain in doing this, and at the end again, because of the regular routine, that checkup, you could not manage this one. But definitely, it's a wonderful opportunity for all of us, and definitely we look forward for future the interaction again online, person to person, in person, maybe some of the other situations and other events.
Yes, that would be excellent. And so maybe we can try to sometime arrange a meeting where we can discuss, maybe some follow-up or maybe some potential interactions even. I think that would be very interesting to think about.
Yes, yes. So we have Professor Bobby Krishna, who is the convener of this talk. So Professor Krishna.
Actually, Dr. Mark, we could not believe after seeing your video. We are thinking that you are speaking live.
Well, that's good. Yeah, because so I just recorded that.
Nice.
So the recording went well. That's good. Yeah. And so
it's very good.
Very good. We've been following that approach on some of the other classes where we've been doing online versions. So the recordings have actually been quite valuable, especially when you have all the schedule disruptions and whatnot. So glad to hear that you were able to actually view it well and it came through fine. So that's good.
Yeah. So, thank you very much.
Probably getting awful late. Yeah, probably getting awful late over there on your end, but yes, it would definitely be good. Look forward to maybe you could set up some other kind of a follow-up meeting and maybe see if there's some interesting kinds of interactions. And it's very unfortunate we weren't able to host your trip to visit us. I guess it's already a year ago now. We were planning to try to see if we could arrange a chance for you to visit us over here. But yes, I think we should definitely try to see what we can come up with.
But good. Anyhow, your video was received very well. And thank you to Dr. Gaurav Nanda. He had covered the question answer session very well. So we are feeling that Dr. Mark Leto is really replying. So he replied very well to all the questions because he knows the subject.
Professor Nanda is clearly very familiar with the work, so I think that he should have been able to answer the questions. So I'm glad to hear that. Okay, well. Were there any? Do you have any other questions? If not,
anybody want to ask any question from the audience? Because this is totally research-oriented talk. All the researchers academicians are in the audience. Ashish, Abhi, you want to ask any question?
Yeah. Dr. Das, you want to ask any question?
See, apart from your research, Dr. Mark, the data is very interesting to me. See, I am one of the experts in the walking at height. I know that low-fall injuries are more across the world, but in India, I could not get much data collected. But it's good that you have shown the low-fall injuries are that's the biggest data in the CoE-SEA, your project. It supported my thinking that in the projects, in the industries, people should pay very good attention for the low-fall injuries. People try to neglect low-fall and they used to concentrate only on high-fall. And that's a very good thing, observation which I could see. If that's again a research topic, if somebody could work on that and get some prediction applying machine learning tools on the low-fall injuries, that would be very useful for the industries.
Yeah. This is actually something that could maybe be explored as some other. I know with countries like India and others to explore ways of expanding data sets and sharing data between different locations. And so I think that's something to think about in the future. Are there some routes that could be followed to try to do that? And so clearly, another opportunity area is to expand the collection capabilities within India, and thinking about, what are some strategies that could be followed to best obtain information based on the lessons learned in other locations. So I do think that's a exciting potential opportunity, and especially I think some of the organizations like WHO and others, I think, would potentially be quite interested in trying to support such work. And so thinking about maybe there's some ways that we could try to make some progress in that direction would be of interest and very useful.
Thank you. Thank you, Dr. Leto. Thank you, Dr. Gaurav, for this excellent presentation. And I also thank the critical mass of the audience. See, a lot of calls since morning I got, this is highly researched. We may not be able to understand, that's why we may not attend. See, industry partner, there are many industry partners in this. Now they are very, the audience are looking what sort of talks are coming, very interesting. My scholars, research people, academicians, it's very, very interesting talk. Thank you very much. And the moderators, Mom and her team, you did a very good job. And Professor Maiti, we should look for one more topic for Dr. Mark in the near future, so that we can really see physically him speaking on the topics.
Sure.
Thank you all. Thank you for the session. Thank you very much.
Yeah. Thank you, Professor Mark. Thank you, Professor Nanda.
Thank you, Professor Maiti, and thank you very much, Professor Krishna. Yeah, it was great again to interact with everyone. So, yeah.
Yeah, and we would look forward to trying to expand future interactions, like I said, and there's many routes. The online routes are maybe the easiest for now, but as some of the disruptions go away, hopefully we'll be able to maybe even get some face-to-face types of interactions. That'd be good.
Good. Thank you. Thank you and bye-bye.
Yeah, thank you and bye.
Okay, thank you everyone. Thank you participants.
Thank you.
Thank you. Bye.